As we said at the beginning of this chapter, engineers need to understand the whole relationship between a space of input signals and the corresponding space of output signals. They need to understand how a system responds to a broad range of input signals, not just to be able to solve a differential equation if they're given a specific input, a specific forcing function. And that's what we're going to do in this part of the course. We're going to study the responses of LTI systems with a view to gaining that sort of understanding. Now, we've seen that the mathematics work out to be much simpler if we work in the Laplace domain, which is an example of what we often call the frequency domain. So that's what we're going to do in this course. We know that the transform of the response of an LTI system is equal to the product of the transfer function h of s of the system with the transform f of s of the input. And again, in this part of the course, we won't be focusing all that much on specific inputs. We're really going to be looking at the transfer function h of s and the way it determines the form of the response. We know that the transfer function is by definition the transform of the impulse response. That is the zero state response to a unit impulse function. And we can see again from this equation that if f of t is a unit impulse, then f of s will be 1. So h of s will be the transform of the response of the system. And, because of that, this equation tells us that the response of the system is the convolution of the impulse response with the input. So in a sense, if you know the impulse response, you know everything there is to know about the way the system responds to any input you might wish. So we'll certainly look at the form of the impulse response of a system with a given transfer function h of s. But now, a unit impulse is not the easiest signal to generate. In the continuous time setting, it's an infinitely high, infinitely narrow spike. So on a test bench, it's often a lot easier to generate something like a unit step input. So we'll look at the responses to unit steps as well. But we won't be considering too many different inputs. We'll mainly be focusing on the form of the transfer function and the way it affects the response of the system. For a simple example, let's talk about how we would compute the impulse response. So again, in the case of the impulse response, f of t is a unit impulse, so its transform is just 1. So in order to find the response y of t, all we have to do is to invert h of s, the transfer function. Now, how do we usually go about inverting Laplace transforms? We're going to be dealing with systems whose transfer functions generally just take the form of rational functions. So we will be doing this inversion the usual way using partial fractions decomposition or partial fractions expansion. And to do this, we factor the denominator of h of s, assuming h of s is rational. So we'll get one factor for every root of the denominator, and the roots of the denominator are once again called the poles. So we get a factor for each pole. So we'll see that the poles of the transfer function are very important in determining the response of a system. The zeros, the roots of the numerator, are also important, and we'll look at their effect as well. I would say there's a particular reason why we're really interested in the effects of poles, and we'll see an illustration of that shortly. The fact is that when you're designing control systems for a given system, you can, in fact, in a sense, shift its poles around. And so we're in particular going to be studying the relationship between the positions of the poles of the transfer function on the complex plane and the behavior of the system, the form of its responses. So let's look at an example. So suppose we have a mass spring system with no damper. Then it might obey an equation of this form: my double dot, the mass, times the acceleration, plus the spring constant times the displacement equals an external applied force F. So let's suppose that we're perhaps interested in doing position control. So the output that we're interested in is the displacement y as a function of time. And suppose that the input of our system is going to be the applied force as a function of time. Now recall that for a system, you have a unique output signal for every input signal, because a system is defined as a mapping or a function. In order to get that uniqueness, we have to specify initial conditions, and we're typically going to be assuming that all initial conditions are zero valued. So we'll be looking at the so-called zero state response. That will give us something that satisfies the definition of a system. So let's take transforms with zero valued initial conditions. As we said at the end of the previous lecture, this is how we normally find transfer functions. So what do we get in this case? Well, the transform of the second derivative, if all of the initial conditions are zero valued, is simply s squared y of s by our differentiation property. If you ignore the initial conditions because they're zero valued, then every derivative simply corresponds to multiplying by s. So if we solve for y of s in this equation, we get 1 over ms squared plus k times f of s. This describes the zero state response of our system, and in particular this function here, by which we're multiplying f of s, is our transfer function. So suppose we want to find the impulse response of this system. What that's going to tell us really is the effect of in this case of imaginary poles. Normally we factor, of course, the denominator of the transfer function, which, by the way, is often called the characteristic polynomial. That's terminology that's used in differential equations as well. We factor the characteristic polynomial. According to the roots, we're getting a different factor for every pole, and that way each pole will contribute a term to the response of the system. So for simplicity, suppose we want to find the impulse response. So what we can do is take the transfer function h of s and for simplicity, let's divide both the numerator and denominator by m, so we get 1 over s squared plus k over m. Okay. And then what are the roots going to be? You'll have one root at j times the square root of k over m, and another at minus j times the square root of k over m. Anyway, this is a difference of squares, so we get s squared minus the square of j times the square root of k over m. Sorry, did I say we get s squared minus the square of j times the square root of k over m, which of course gives us s squared plus k over m. Now we could do a partial fractions decomposition. If we skip that stage, you know that we're going to get exponentials that are going to have, in this case, imaginary exponents. In fact, we're going to get that h of t equals 1 over the square root of mk times e to the power j times the square root of k over m t. This corresponds to the first of our poles in our factorization, minus e to the minus j times the square root of k over mt, and that'll all be divided by 2j. So in fact, this is a sinusoid here. This is a sine. But we get an exponential for every root of the denominator of the transfer function, that is, for every pole. And this is why the poles are so important in determining the form of the response of the system. In this case, f of s itself doesn't have any poles because we're looking for the impulse response, so f of s is just 1. So all of these terms of the solution simply come from the transfer function itself. So they reflect, if you like, the intrinsic dynamics of the system. So these poles at plus or minus j times the square root of k over m reflect what you might call the intrinsic dynamics. They don't result from the input, which is simply an impulse. In this case, those intrinsic dynamics correspond to a kind of physical resonance, because this is an oscillatory response. It's a sinusoid. And resonances like this are sometimes called natural frequencies. This is a natural vibrational mode of the system itself. So in fact, you can think of poles as a kind of generalization of this idea of a natural frequency. Natural frequency is the term that physicists often use for this kind of phenomenon. So again, the idea here is that poles capture key features of the intrinsic dynamics of the system. And in this case, again, you can rewrite the impulse response as 1 over the square root of mk times a simple sinusoid. So it's the sine of the square root of k over mt. So the imaginary part of the poles is plus or minus the square root of k over m, and that imaginary part of the poles, in fact, gives us the angular frequency of the oscillations. And we'll see that this is generally the case. If you have complex poles, then their imaginary part typically represents the angular frequency of some oscillation that you observe in the response of the system. I should emphasize maybe that this is the angular frequency, that is in radians per second. If we were talking about the ordinary frequency in hertz, if you like, it's going to be 1 over 2 pi times this. So that's the frequency in cycles per second. So that's a particular example where we were looking at the impulse response of a simple system, system with a simple so-called first order, that was a second order transfer function because it has 2 poles. What if we have a more general input? Well, then we're in general going to have other poles of the transform of the response, because y of s will be h of s times f of s, and f of s will have poles of its own. So the form of the response will reflect both h of s and f of s. But it's particularly important for us to investigate these phenomena, if you like, of natural frequencies of systems, and in particular to understand the effect of the poles of h of s on the form of the response. Particularly important for us to understand the effects of the poles and zeros. Essentially because that's what we can control, that's what we can alter. Either by maybe altering the system itself, or more commonly, as you'll spend some time studying in SE 380, by adding feedback to the system, putting a feedback loop around the system with this transfer function h of s. And we'll see an example of what that does before very long. So to do this, we're going to use a couple of so-called test signals. We'll mainly just look at the cases where the input, f of t, is a unit impulse or a unit step. So we call these respectively the impulse response and the step response. Of course, we know that the responses to any input are determined by the impulse response. You just have to convolve the input with the impulse response in order to get the response to the input. But in this case, there's a particularly simple relationship. What do you suppose is the relationship between the impulse response and the step response? In the case where the input f is an impulse, we know that y of s is just equal to the transfer function itself. In the case of a unit step, of course, you have to multiply the transfer function by the transform of a unit step, namely 1 over s. So the transform of the step response is 1 over s times the transform of the impulse response. What does that tell us about the relationship between the two responses in the time domain? by our, maybe pause the video if you want to think about it yourself, spoiler alert, by the differentiation and integration property of the Laplace transform, multiplying by 1 over s in the Laplace domain, at least in the case where all initial conditions are 0, amounts to integrating in the time domain. So the step response is just the integral of the impulse response. But again, the step response, the unit step input, tends to be something that we can more easily generate on a test bench. I understand that people who work on a lot of mechanical systems, like mechanical engineers, they sometimes use impulses in the lab, or they approximate impulses by hitting things with large hammers. But generally in electrical engineering applications, step input is something that's a little easier to generate. So again, we're interested in particular, in looking at the effects of poles on the form of the response. And in order to understand those effects, we really just need to look at a couple of key examples from which we'll be able to extrapolate. So we'll look at a standard first order example, that is a system with only one pole. Of course, if all of the parameters of our systems, all of the constants in the differential equations and the transfer functions that model our systems are real valued, then the poles, the roots of the denominator of the transfer function, or the roots of the characteristic polynomial, have to be disposed symmetrically about the real axis. So if there's only one such pole, it has to be on the real line. So the case of a first order system will show us the effect of a real pole on the response. We'll then look at second order systems so we can see the effects of complex poles. And then we'll just be able to extrapolate from there, essentially. We'll look at the effects of zeros as well, and then we know that we can factor any polynomial into a product of linear and quadratic polynomials, and perform partial fractions decomposition. So we can sort of decompose higher order transfer functions into first and second order transfer functions, into sums of first and second order transfer functions. So we're going to start by looking at the so-called standard first order system. And I think we'll look at that in a separate video just to keep from making our videos too long. So I'll simply tell you that what we mean by the standard first order system is going to be this one right here. K over S tau plus 1, where we'll assume that K and tau are both positive real valued constants. We'll see why in the next lecture, but K is what we call the DC gain of this transfer function. But DC gain is a general concept that applies to transfer functions of other forms as well. And for reasons that we'll see in the next video, we call tau the time constant. You know already, because this has just a single real pole, that the impulse response, for instance, is going to be an exponential. In the case where tau is greater than 0, it's going to be a decaying exponential. And the value of tau determines the rate of decay. That's why we call tau the time constant. But we'll look at this example in detail in the next video. See you there.